Today we are going to extend the direct stiffness approach to building frames incorporating the effect of the floor slab. In general, all buildings, whether low-rise or high-rise, they have the presence of the floor slab. And the structural system we adopt depends on the height of the structure. Typically for 8 to 10 stories, simple frames, they are sufficient to take care of both the vertical and the horizontal loads. For higher number of stories, generally a combination of shear walls and frames is used. Typically these buildings, they have lifts, so lift cores, they serve the dual purpose of providing service and also as structural elements in the form of shear walls. But for very tall structures or high-rise buildings, we need to adopt a very special structural system. Typically we may adopt a tube kind of structure. Tube structure is basically a system comprising of closely spaced columns, or we may have tube inside tube. So we are going to organize a special talk on high-rise structures as an extracurricular activity in this course, and that talk will cover on the analytical aspects and the practical aspects of high-rise buildings. We have already learned how to incorporate 3D analysis in our framework. All we have to do is we consider 6 degrees of freedom now at each joint, 3 rotations and 3 translations. So the stiffness matrix is now 12 by 12 for each member. We introduce the additional term involving torsion, and also we have to take care of IY and IZ depending on the plane of the bending. Now this is called as the general 3D analysis. So the general 3D analysis, it helps us in automatic distribution of the vertical and lateral loads among different frames and their constituent members, such that we don't need to do any superposition after the analysis is done. It is very rigorous and it gives us an output which is very compact. All the member and forces, they are 12 by 1, and all the joint displacements, they are 6 in numbers, so we get everything. But then the point is that this general 3D analysis, it ignores the presence of the floor slab, especially its role in lateral load distribution. It only considers that slab is made up of plate kind of elements and they have the role in vertical load distribution, that is, they do the distribution of the vertical gravity loads among the various beams. And we may also include the effect of slab as the flange part of the beam. Beyond this, the effect of the slab is totally ignored. But the true fact is that floor system does offer structural functions also. It helps in the distribution of vertical loads to beams through bending. It helps in the distribution of the lateral loads by in-plane action. So in-plane action means that it binds all the beams surrounding it. So it enforces a special compatibility condition. So these effects, they need to be considered rigorously. So far we have ignored these effects in the analysis. Now there are 2 ways of considering it. One way is that we just employ a general 3D analysis software and we model the slab elements as plate elements. Other is that we devise the formulations of the members, especially the members which are in a horizontal plane, which are part of the floor system. Their stiffness matrices are modified such that the effect of the slab is automatically taken care of. So in this course, we will be using the approach of modifying the formulations. Now let us see the difference in the behavior of the frames when we consider floor slabs and when we ignore it. So the top structure is a 3D structure where there are 3 frames, 1, 2 and 3. It's a symmetrical structure, means frame 1 and frame 3 are identical, and we are deliberately applying the force at the column of frame number 2. The deformation pattern of the structure would be like this. So what we can observe is that frame number 2 is undergoing larger deflection because the force is concentrated at frame number 2 only. And we can also observe that the beams have undergone lateral bending. So here the compatibility is a bit different. The axial forces will be generated in the beams and there will be lateral bending of the beam. So it is like a non-uniform distribution of the lateral loads. On the other hand, if we consider the structure like this, where there is a presence of the floor slab, then the load applied at this particular point will lead to a uniform translation. So what difference this slab has created is that it has bound all the frames together, and the compatibility condition has ensured that all the frames, they undergo same amount of lateral displacement. So the forces will be distributed among the frames in proportion to their individual stiffnesses. What will happen in case this force were acting at corner? Now in this particular case, the presence of the slab will lead to a compatibility condition that the deformation of the structure would be like this. So what we can observe is that it has undergone a torsion in the horizontal plane. So this compatibility condition is brought about by the slab. So that's why it's very important to include the effect of floor slab if it's present in the analysis. Otherwise, we may get misleading results. We may find that the beams, they are undergoing lateral bending, and we may also find axial forces in the beams. If floor slab is not there, or if it has large cutouts, then definitely we need to design the beams for lateral bending and for axial forces. But if a rigid diaphragm slab is present, then it will have a different effect on the behavior. Now here there is an option that we can replace the 3D analysis by a simplified plane frame analysis. So if the building is symmetrical and if the loading is also symmetrical, then we can do an equivalent plane frame analysis like this. So here the 3 frames, they have been repositioned in series and they are just connected by rigid links. So this enforces the compatibility condition that all the frames, they undergo same amount of displacement, provided frames 1 and 3, they are identical. So the structure has a uniform translation without any rotation. So in this particular case, we can find out how much force is carried by each frame in terms of the reactions we get at the bottom. So typically if we find out the reactions at the bottom, we should be able to find out how much is the force each frame carries. So let's say this frame number 1, the reactions, they sum up to F1. Frame number 2, the reactions, they sum up to F2. And frame number 3, the reactions, they sum to F3. So F1 and F3, they would be same because the frames are identical. So all the 3 frames, they are undergoing same amount of displacement, and we can find out the stiffness of the frames also because we know how much force each frame is carrying. And if we find out the displacement, then the ratio of the force to displacement gives us the stiffness of the particular frame. However, this analysis will not be valid if our structure is a bit different. However, the analysis will not be valid if our structure is unsymmetrical or if the loading itself is unsymmetrical. So in these 2 cases, we need to perform rigorous 3D analysis duly considering the effect of the floor slab. So in this particular course, we will derive the formulations necessary for this purpose. In such a situation, we need to carry out a full 3D analysis, rigorously taking into account the effect of the floor slab. So in the coming lectures, we will be deriving the formulations appropriately. Now before we do so, let's write down the assumptions. So our first assumption is that the slab is monolithic with beams and columns. Then it is a continuous slab, no large cutouts. If there are large cutouts, then this analysis will not be valid, and in that particular case we may just analyze the frame itself, and in that particular condition the beams need to be designed for axial forces as well as for lateral bending moments. Number 3, we assume that all joints, especially the unrestrained joints, they lie on floor slabs. This assumption is important because we will be dealing with the displacements at a particular reference point. That's why it's very important that all the joints, they are lying on the floor slab only. Number 4, we assume that the slab is sufficiently thick so that rigid diaphragm action results. Number 5, all other assumptions of the direct stiffness approach, they are valid. So if we are considering non-prismatic members, if we are dealing with deep beams or such members, then we must rigorously consider the treatment which we have learned for non-prismatic members as well as for the shear deformation effect. To highlight assumption number 4, it's further emphasized that the analysis shall be valid for RC structures with sufficiently thick floor slab. So it will not be valid for steel frames with sheet-based roofs. For example, in the case of the shed structures or in the case of the frames with sheeting, the stiffness of the floor slab is not enough to enforce rigid diaphragm action. So the implications are that the points lying on the floor slab, they undergo rigid body translation and rotation. Beams will not have any bending in the plane of the slab and there won't be any axial deformation in the beams. So typically if we want to observe how the floors, they will undergo deformation, let's say if we have a floor in the XY plane and then under the action of the loads, it will undergo a combination of the displacement and rotation. So it is as though there is a reference point and this reference point is undergoing a horizontal translation as well as a rotation in the plane of the floor slab. Or alternatively, we may consider that basically the entire slab system is undergoing rotation about some external point. So in both ways we can consider the modeling. So we will now derive the formulations so as to implement these points. So as we have already noted, we generally consider the translation and rotation at our reference point. So now our numbering scheme will be a bit different. Typically what we are considering here is that the floor slab undergoes displacement like this. So it undergoes a combination of the translation and rotation as shown in this animation. So what we do is that we consider the lateral degrees of freedom and the rotation of the floor slab at reference points only. So what we have done is that the horizontal translation in the global x direction, the horizontal translation in the global y direction, and the rotation in the horizontal plane about global z direction, they will be associated to the particular reference points. So these reference points, they could be lying in one vertical line or they may be lying at different locations, but it's convenient if these reference points, they all lie at one particular vertical line. So once we have the displacements and the rotations at the reference point, then on this basis the displacements at any other point can be known. As a result of this, since we have already considered 3 degrees of freedom common, out of the 6 degrees of freedom we only show remaining 3 as the joint degrees of freedom. So typically a joint has 6 degrees of freedom. Now 3 degrees of freedom, 2 translations and 1 rotation has been considered at the reference point. So we need not consider these at the joint. So at the joint we consider only the remaining 3 degrees of freedom, 2 rotations and 1 translation. So together we call these as the joint degrees of freedom, and the degrees of freedom associated with the floor, they are called as the floor degrees of freedom. So let's do here a marking exercise. Let's say that we are numbering the joints as 1, 2, 3 and 4 for the first floor, and for the second floor we are beginning the numbering from 5. 6, 7 and 8. And now we do the numbering of the degrees of freedom. 1, 2 and 3. 1, 2 and 3, they are already marked, and we do the marking such that we first mark the vertical displacement and then we label the two rotations. So following this order, we have here 4, 5 and 6. So 4 is the translation in the vertical direction, 5 is the rotation about the global x-axis, and 6 is the rotation about the global y-axis. Then similarly we have 7, 8, 9, then 10, 11, 12, 13, 14 and 15, 16, 17, 18, 19, 20, 21 and 22, 23, 24. So we have now labeled all the joint degrees of freedom, and after this now we come to the floor degrees of freedom. So the next numbering will start from 25. 25 is the horizontal translation of first floor in the x direction, and 26 is the translation in the y direction, and 27 is the rotation about the global z axis. And similarly we have 28, 29 and 30. So after we have done the numbering of all the degrees of freedom associated with the joints and the floors, then we do the numbering for the degrees of freedom associated with reactions. So we have 31 to 36, then we have 37 to 42, then we have 43 to 48, and from 49 to 54. So this is how we would do the numbering of the degrees of freedom. So it's different from the numbering we have followed so far. So this is how the numbering will now look like. So the choices of the reference points O1 and O2 here is a bit arbitrary. So all the displacements, they are transformed to this point. Similarly, we will be transforming the forces also to this point. Another implication would be that the total degrees of freedom will be different from the usual general 3D analysis. If we had the general 3D analysis, because there are 12 joints, the size of KTS would have been 72 by 72. But here in this particular case, the size of KTS is 54 by 54. So this number is given by this expression, that first we have to find how many unrestrained joints are there. Each unrestrained joint has 3 joint degrees of freedom. Then we need to find how many floors are there. Each has 3 floor degrees of freedom, and then there are degrees of freedom associated with the reaction. So it will be less than 6n in the case of the regular 3D structures. So with this, the formulations we will be beginning in the next class. Before we leave, let's hear one question asked by a student in one of the previous years. So thank you very much. Any other question? Go. His question is that now beams do not have any axial force. So where axial force go? Let's say we are applying some force there. What element is absorbing the axial force? Let's say the earthquake forces are there. We have applied at the joints. Essentially, where are they going? They are not going in the beam. So where they are going? Column, okay, but then at for floor level column they will not go automatically. Basically they will come as axial force in the slab. But slab area is so large that if you convert it to stress, it will be very small. You calculate, for example, you have 150 mm thick slab and you calculate the area frame to the total width of the whole. Just do this calculation for this room itself. If let's say your slab
this structure would be at least 200 mm or maybe 250 mm. Usually this level of structures, they have thick slabs, so 200 mm slab, and you see frame to frame spacing, how much is the frame to frame spacing. So it will be typically 5 to 6 meters. So 6 meters into 0.25, how much is the area? Roughly it's 1.5 meters square. That's very big area. So all the axial force, we assume it's absorbed there. Okay.